Section 6.3, Taylor and Maclaurin series. All of this information is from OpenStax Calculus Volume 2. I suggest you go check that textbook out. At the bottom of every page there is a link directing you to where you can download the full text. And again, I suggest you do that. In this section, what we are concerned about, our main concern, our main goal, is writing a power series representation for any function. So in previous sections we've seen that, particularly the function 1 over 1 minus x, we can take what we know about that function as a geometric series and sort of manipulate it to write some other rational functions and things. But what if we have a generic function, just f of x? Just kind of go with me on this. Okay, if we have f of x equals this power series. Okay, well, if we evaluate, and it's in the expanded form on the right, but if we evaluate this series at x equals a, then you can see all of these terms, all the terms following the first, past the 0th term, are going to be 0. So we see that f of a is equal to c naught. I'm going to go ahead and write it this way. C naught equals the 0th derivative evaluated at a divided by 0 factorial. In this case, 0 factorial is 1s, and this is just f of a. Okay? Well, because we can take derivatives term by term, we can then see that f prime of x has this power series representation. N times cn times x minus a to the n minus 1. And so here's the expanded form, and if we evaluate each of these at x equals a, 0, 0, 0, and on, which allows us to see that f prime of a is just c1. And again, I'm going to write that in this way, which that is just f prime of a divided by 1 factorial, which is just 1. Continuing on, we take f double prime is n times n minus 1 times the rest that's familiar. Expanded form we have here. If we evaluate at x equals a, every term here is 0, except for f double prime being 2 times c2, our coefficient. Rearranging that, we see that c2 equals f double prime of a divided by 2 factorial. The third derivative, also, again, if we follow the same pattern, evaluating or taking the third derivative term by term, n times n minus 1 times n minus 2, there it is, evaluated out. We take x equals a, every term except for the first here, because we have constants at the beginning that are falling off here. We see that f, the third derivative of f evaluated at a, is 3 times 2 times c3, meaning c3, third coefficient there, is the third derivative evaluated at a divided by 3 factorial. Now, if you kind of trace these down, you'll see there's a pattern. In general, we can see, and I'm going to scratch this off. In general, we can see that the coefficients, the nth coefficient that is the nth derivative of f evaluated at a divided by n factorial. And we want to summarize that in our definition of Taylor and Maclaurin series. If f has derivatives of all orders at x equals a, then the Taylor series for this function is the series from 0 to infinity of the nth derivative of f evaluated at a divided by n factorial times x minus a to the nth power, which we see is f of a plus f prime of a times x minus a plus the second derivative at a divided by 2 factorial times x minus a squared plus, and it continues on. Now, if this is centered at 0, we call this the Maclaurin series. Now, based on our previous sections, particularly the last one, we know that the power series for any function is going to be unique, and thus Taylor series are unique. So we have this in a theorem. If a function f has a power series at a that converges to f on some open interval containing a, then that power series is the Taylor series for f at a. Now, as we look at a Taylor series, but really any series, we look at the sequence of partial sums. And we should notice in this case that with a Taylor or a Maclaurin series, these partial sums are polynomials. And so we define these as Taylor polynomials, or Maclaurin polynomials, as the case may be. If f has n derivatives at x equals a, then the nth Taylor polynomial for f at a is Pn of x, and often this is denoted Tn of x for Taylor polynomials. We have f of a plus f prime of a times x minus a plus the second derivative at a divided by 2 factorial times x minus a squared, etc. Continuing on that pattern. So in this form, each term is of that form. So let's go ahead and find some Taylor polynomials. We have the function f of x equals natural log of x, and we are centered at x equals 1. So this will require us to look at several derivatives, in this case 3 derivatives, and then evaluate each of those at 1. So f of x is natural log x. So f of 1, because we are evaluating this one at 1, is 0. F prime of x is 1 over x, and so f prime of 1 is 1. The second derivative, negative 1 over x squared, and so evaluating the second derivative at 1, we get negative 1. The third derivative of x is 2 over x cubed. So the third derivative evaluated at 1 is 2. Alright, so P0, our 0th polynomial, is just f of a, so 0. Our first Taylor polynomial is 0 plus, and now we have 1 divided by 1 factorial times x minus a, in this case 1. Now you're going to notice that is just x minus 1. That is all the first Taylor polynomial is. So the second polynomial will take x minus 1, the last polynomial, plus, well in this case minus, because we have a minus 1 here, minus 1 over 2 factorial times x minus 1 squared, which I will write as x minus 1 minus 1/2 x minus 1 squared. Now our third polynomial, x minus 1 minus 1/2 x minus 1 squared plus 2 over 3 factorial x minus 1 cubed. Okay, well that means our third polynomial is x minus 1 minus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed. Now if we compare these polynomials, each of them, to the original function, natural log of x, at the value 1, they all have a common value at x equals 1. So as n goes to infinity, as we take the further polynomials we go, Pn of x appears to converge to f of x. Let's call it f of x. Okay. Close to 1. If we're close to 1, our Taylor polynomials are very, very good approximations. All right? And we can use that to our advantage in some other cases. For each of these following functions, find formulas for the Maclaurin polynomials P0, P1, and P3. And we'll go ahead and add P3 in there, or P2. Find a formula for the nth Maclaurin polynomial and write it using sigma notation. Use a graphing utility to compare the graphs of the polynomials with f of x. Okay, let's begin with just f of x. Well, we have it given here. So f at 0, because these are Maclaurin, we are centering at 0. That will be 1. F prime of x is e to the x, so f prime of 0 is 1. And you might notice very quickly, this is going to be the same. Okay, so f double prime of 0 is 1, f triple prime of 0 equals 1. So our polynomials, we'll go ahead and write these. Our 0th polynomial is 1. Our first polynomial is 1 plus 1 over 1 factorial times x, and we'll just have x because we're centering at 0, so x. So this is 1 plus x. Our second polynomial, 1 plus x, plus 1 over 2 factorial x squared, which is just 1/2. P3, 1 plus x plus 1/2 x squared plus 1 over 3 factorial times x cubed. All right, so in general, the nth Maclaurin polynomial, our Pn, and since we're using the nth polynomial, we better start with a k there. 0 to n of x to the k divided by k factorial. That should be the closed form of our nth polynomial there. Now if we carry these out and we graph them, compare them, at 0, again, all of these agree at 0. But around 0, close to 0, they are all very good approximations. That's kind of the idea here. We're finding a function that represents our function, or a power series that represents our function at a close range of something. Now, as you take this out to infinity, there's a good chance that our infinite polynomial is going to match up, which is, again, our big goal here. All right, sine of x. All right, well, f of x is sine x. So f of 0, because we're Maclaurin polynomials, is 0. F prime of x is cosine x. F prime of 0 is 1. F double prime of x is negative sine x. So our f double prime of 0 is 0. Ooh, let's try that again. All right, f triple prime of x is then negative cosine x. And so evaluating that at 0, we have negative 1. All right, so our 0th Taylor polynomial will just be 0. Our first Taylor polynomial is 1 over, we're just going to leave off the 0, 1 over 1 factorial x, which is just x. Our second Taylor polynomial is going to be x plus 1 over, or 0 over, 2 factorial times x squared, which is still going to be x. All right, our third Taylor polynomial is x plus, and we will have negative 1, so we'll have a minus there. All right, we know we'll have an x cubed. We'll have a 1 over 3 factorial. Let's just go ahead and carry this out a couple more. P4 and P5. P4, x minus x cubed over 3 factorial plus, and that would be 0 for the next one. So actually that is our polynomial there. Now the fifth derivative is going to be 1 again. So x minus x cubed over 3 factorial plus 1, or x to the 5th, and this time it'll be 5 factorial. So every other polynomial is actually the same. All right, so let's go ahead and write a closed form for Pn. All right, we'll go k equals 0 to n. And this is alternating, so negative 1 to the k. And these are all odd exponents, if you notice. x, x cubed, x to the fifth, etc. So x to the 2k plus 1 divided by 2k plus 1 factorial, because if you notice, our denominators are doing something very similar. They always match. There is our nth term power series. Now, if we let n go to infinity, then we would be at sine x. Okay, now let's compare these polynomials. And again, close to 0 in this range there, things look very good. All right, cosine x. We're going to have a very similar idea here. Right, f of 0 is 1. F prime is negative sine x, so f prime of 0 is 0. Second derivative, negative cosine x, so the second derivative at 0 is 1, negative 1. Our third derivative will be sine x, so the third derivative evaluated at 0 is 0. If you notice, we have alternating, but in a slightly different form. So we'll go ahead and write these out. The 0th polynomial is 1. It's just f of 0. The first polynomial is 1 plus 0 over 1 factorial x. This one's going to be 1 plus, we'll do to the second there. All right, so this will actually be a minus 1 over 2 factorial x squared. The third polynomial, 1 minus 1/2 x squared plus 0 over 3 factorial x cubed. The fourth polynomial, I'll go ahead and go out a few more again. This is going to be 1 minus 1/2 x squared. That would be a positive 1, so plus 1/4 x to the 4. Actually, it'd be 4 factorial. Okay, I'll just go ahead and leave the factorial there. So, in general, it appears that our nth Taylor polynomial is going to be negative 1, we're still alternating, to the k, is x to the 2k, because they are always even, and then we have 2k factorial, again, because they're always even. Now let's compare these polynomials. Again, in the neighborhood of 0, things are looking very good. Alright, so now we've come up with the idea of making the polynomial, the question then becomes, how do we know that these power series we're coming up with are actually approximating that function, that they're converging to each other, or that the power series is converging to that function? How do we know that? And so we next come up to this idea. So recall that the nth Taylor polynomial is the nth partial sum. We define the remainder, Rn of x, to be equal to f of x minus Pn of x. Thus, if the Taylor polynomials Pn of x converge to f of x, the remainder converges to 0. And we can estimate the error, okay, how far they are apart, with this next theorem, Taylor's theorem with remainder. So let f be a function that can be differentiated n plus 1 times on an interval I containing the real number a. Let Pn be the nth Taylor polynomial of f at a, and let Rn of x equal f of x minus Pn of x be the nth remainder. Then for each x in the interval I, there exists a real number c between a and x, such that Rn of x is equal to the nth derivative, or the n plus 1th derivative, evaluated at whatever that value c is, divided by n plus 1 factorial times x minus a to the n plus 1. If there exists a real number m so that the derivative is constrained for all x in that interval, so that we can say the absolute value of that is less than or equal to m, then the absolute value of Rn of x is less than or equal to m over n plus 1 factorial times the absolute value of x minus a to the n plus 1. Now, at first glance, that looks really overwhelming. It just does. So let's see if we can use it quite a bit. All right, so consider the function f of x equal to the cube root of x. Find p1 and p2, the first and second Taylor polynomials, at x equals 8. And then we'll compare the graphs of those to the function that we have. Okay. F of x equals x to the 1/3. So f of 8 is 2. F prime of x is 1/3 x to the negative 2/3. So f prime of 8 is 1/12. F double prime of x is going to be negative 2/9 x to the negative 5/3. Meaning the second derivative evaluated at 8 is negative 1/144th. So let's attempt to write our polynomials. P1 is f of 8 plus f prime of 8 times x minus 8. Which means we have 2 plus 1/12 x minus 8. All right, P2 of x is f of 8 plus f prime of 8 times x minus 8 plus f double prime evaluated at 8 times x minus 8 squared. Which means we have 2 plus 1/12 x minus 8 minus, once we divide by our 2 factorial there, this will be minus 1 over 288 times x minus 8 squared. Actually, I'm not going to compare the graphs here. We did that plenty before, so ignore that. All right, now let's use those two polynomials to estimate the cube root of 11. So what we'll do is we'll evaluate each of those. Okay, our P1, we'll evaluate that at 11. That is 2 plus 1/12 x minus, well, our x is 11, so 11 minus 8, which is 2.25. Okay, there's our approximation. So P2 of 11 is 2 plus 1/12, 11 minus 8, plus, actually in this case it is minus 1 over 288 times 11 minus 8 squared. And that is equal to 2.21875. Now the idea though that we want here is, can we bound the error? Can we guarantee that we're within a certain range? So with Taylor's theorem, the error, okay, the remainder of our first term, in this case we'll go ahead and make this at 11. By Taylor's theorem, this is equal to the second derivative evaluated at c over 2 factorial. We're going from the first to the second derivative there, times 11 minus 8 squared for some c in the interval between x, 8, and 11. Okay. Now we don't know what that c value is. So what we want to do is find the maximum value. So if you look at the second derivative, we said that was negative 2/9 x to the negative 5/3. Now that is a decreasing function. So the maximum, so the maximum occurs at x equals 8. There we go. All right, so it's decreasing. So our maximum value is at x equals 8. Okay, so at that point, f double prime of 8 is negative 1 over 144. So that is the highest, the greatest value of that function at that point. So what we can then do is we're going to take this to be our m. Right? F double prime of c is less than or equal to 1 over 144. Okay. So this means our error, R1 at 11, is less than or equal to, all right, let's see, 1 over 144 divided by 2 factorial times 11 minus 8 squared. So our error is less than 0.03125. That is our error bound. So at most, we are 0.03125 off from the actual answer. Now let's find our error bound for our second remainder there, evaluated at 11. All right, that would be f triple prime of some value c divided by 3 factorial 11 minus 8 cubed. Okay, well, f triple prime, okay, of x, okay, is equal to 10 over 27x to the 8/3. It also is a decreasing function, so our maximum value of 0.0014468 at x equals 8. So that is going to be our m value. Okay, the absolute value of f, the third derivative, evaluated at 8, okay, or at any point in there, is less than that m, which means that our remainder error is less than or equal to 0.0014468, 3 factorial, and really we're taking the absolute value here, x, which is 11 minus 8 cubed, and that error bound is then going to be 0.0065104. That is our error bound. And that is what we're after. All right. Now, we saw previously that the Maclaurin polynomials for sine x are given by this form here, this generic form. So use the fifth Maclaurin polynomial for sine x to approximate sine of pi over 18 and then bound the error. All right. Well, based off of that calculation, the fifth Maclaurin polynomial is given by x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, which means if we evaluate this at pi over 18, which is pi over 18 minus pi over 18 cubed over 3 factorial plus pi over 18 to the 5th over 5 factorial. That'll be our estimate, our approximation, so 0.173648. Okay, now to bound the error, that part's simple enough. To bound the error, we want to consider the remainder. Well, ideally, we would want to find the remainder of this at pi over 18. However, the sixth Taylor polynomial is exactly the same as the fifth, so that doesn't actually help us any. So we're going to go to the next distinct polynomial, and that is the seventh. So we're going to actually find the remainder, the sixth remainder there. So that is going to be f, the seventh derivative, evaluated at some c over 7 factorial x minus 0. So we'll have pi over 18 to the 7. Now, this doesn't seem like it helps because we need to come up with a bound for the function. Well, if you recognize that the 7th derivative of sine is either going to be sine or cosine, which is always bounded by 1, then the absolute value of this remainder is going to be less than or equal to pi over 18 to the 7 over 7 factorial, because that is positive there. That is our error bound. Now, that's a pretty good error bound. It's actually a fairly small number, I believe. Let's check that out and see what that is. Pi over 18 to the 7 divided by 7 factorial. Yeah, 9.78 times 10 to the negative 10. And that's a very small error. Now, next question, for what values of x does that Taylor polynomial, that Maclaurin polynomial, approximate sine x to within 0.0001? Well, for any general x, okay, we know that our 5th Taylor polynomial gives us this, 1 over 7 factorial, absolute value of 7, or of x to the 7. We want to know when that is less than or equal to 0.0001. In fact, let's go ahead and say less than. Well, that, by rearranging that, we get absolute value of x is less than 0.907. So as long as our x is, or the absolute value of x is less than 0.907, then we're going to have a very, very close fit, that 0.0001. All right, let's find the Taylor series for 1 over x at x equals 1 and determine the interval of convergence. All right, well, f of x is 1 over x, and we are finding it centered at 1. So f of 1 is 1. F prime of x is negative 1 over x squared. F prime of 1 is negative 1. Second derivative of x is 2 over x cubed. And the second derivative evaluated at 1 is equal to 2. Third derivative is negative 6 over x to the 4th. So evaluating that at 1 is negative 6. Now if you notice, these are actually respectively 0 factorial, 1 factorial, 2 factorial, 3 factorial. So once we actually divide by our n factorial in each of those terms, our Taylor series ends up being 1 minus x minus 1 plus x minus 1 squared minus x minus 1 cubed, etc. So we can write that as, well, it's alternating with terms of x minus 1 to the n, and it's alternating, so we'll have negative 1 to the n. Now, I'm going to go ahead and write this as, actually, we'll leave it that way. Let's not rearrange that any. So that is our Taylor series for f of x equal 1 over x. So let's see if we can find the interval of convergence. That would first require us to take the ratio test. This would be the absolute value of a n plus 1, so negative 1 n plus 1, x minus 1 n plus 1, divided by negative 1 to the n, x minus 1 to the n. Now we know the absolute value is going to wipe out the negative 1 part of that, negative 1 to the n plus 1, negative 1 to the n. So this is going to be equal to the absolute value of x minus 1. Now, by the ratio test, for this to converge, we need this to be less than 1. All right, so because there's no values of n left, we don't need to take the limit there. So our limit is actually that x minus 1 absolute value. So let's take that interval, put that right here. That would be x minus 1 is between 1 and negative 1, which means x is between 2 and 0. So our open interval of convergence is 0 to 2. So we know we have 0 to 2. Now let's check out what happens at x equals 0. At x equals 0, for this, we get the sum n equals 0 to infinity of 1 to the n, which quite obviously diverges. So we don't include 0 in that. Okay, at x equals 2, we get the sum of negative 1 to the n, which also diverges. So we don't include that. So our interval of convergence is 0 to 2. It's an exclusive interval. And our radius of convergence is 1. Okay. Now for this function, you actually could have written that as 1 over 1 minus parentheses 1 minus x. So it could have been geometric as long as 1 minus x is less than 1, which gives us the same interval of convergence. So that's good. Now recall that we say a series converges to a particular value if and only if the sequence of partial sums converges to that value, which is equivalent to saying that the remainder term goes to 0. So we have this, that if it has derivatives on all orders on an interval I containing a, the Taylor series converges to f of x for all x in I if and only if the limit as n goes to infinity of Rn of x, our remainder polynomial, if that equals 0 for all x in that interval. To show it goes to 0, we often use, or we generally use, this bound that we've come up with. And if that goes to 0, then that means Rn of x must go to 0, based on the squeeze theorem. So let's go ahead and look at a couple of these. For each of the following functions, find the Maclaurin series and its interval of convergence. Now, I don't need to find the interval, or the Maclaurin series, because we know the Maclaurin series for this is n equals 0 to infinity of x to the n over n factorial, based on our previous work. So first, let's see where this converges. Let's go with our ratio test. And the ratio test, absolute value of x to the n plus 1 over n plus 1 factorial divided by x to the n over n factorial. That would be an x, and that would be an n plus 1, x over n plus 1, which converges to 0. It converges to 0. So and this is true always, because it doesn't depend on the value of x. So our r is infinity. Our interval of convergence is negative infinity to infinity. So it converges everywhere. However, do we know that it converges to f of x? We don't necessarily know that. So let's see if we can show that the remainder term goes to 0. All right, so the maximum value of any derivative of e to the x, okay, on absolute value of x being less than or equal to some value b. We're just going to pick a number, call it b. The maximum value is e to the b. We are going to make this value equal to our m. That's what we're going to use. That's our maximum value to try out. So the absolute value of Rn of x is less than or equal to e to the b over n plus 1 factorial, absolute value of x to the n plus 1. Well, by the divergence test, and also you might consider the squeeze theorem, this is going to have to go to 0 because we already showed that that series converges. Okay, because that really is this portion right here, this sequence, is represented by this series. Because this series converges, okay, because it converges right here, everywhere, any value of x, then we know that this sequence must go to 0 from the divergence test. Therefore, e to the x is equal to that series. Okay, and that is true for all x. Okay, next let's look at sine x. This will be the last thing we consider. Now we've said that this is represented at x equals 0. Actually, let me go back up here. Close to 0, that is a good approximation. But we just showed that they are equal. That's important to note. Okay, so here, this is approximately, it's represented very well by -1 to the n, x to the 2k, or 2n, plus 1 over 2n plus 1 factorial. Now, if we take the ratio test again, if we take our ratio test, that is -1 to the n plus 1. This will end up being 2 to the x to the 2n plus 3. 2n plus 3 factorial, -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. This is equal to, go ahead and write this as -1 to the n plus 1, x to the 2n plus 3 over 2n plus 3 factorial times, we'll flip over the second part, take the reciprocal there, -1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Which is then equal to, I'm going to go ahead and drop off the -1 to the n. So the -1 term, the absolute value of that is just, well, 1. So this is going to be the absolute value of x squared. And with the factorials, we get left with 2n plus 3, 2n plus 2. And this converges to 0. So, our radius of convergence is infinity. Our interval of convergence is -infinity to infinity. But now we have to see if they are equal. Okay, this does converge, but does it converge to sine x? Well, Rn of x, we want to consider that. This is equal to the n plus 1th derivative evaluated at some c in our interval, plus 1 factorial x to the n plus 1. Now, because any derivative of sine is bounded by 1, we can go ahead and say that the absolute value of Rn of x is less than or equal to x to the n plus 1 over n plus 1 factorial. Now, by the same reasoning earlier, okay, this converges to 0. Therefore, that power series converges to sine for all values of x. X to the 2n plus 1 over 2n plus 1 factorial. All right, that brings us to the end of this section on Taylor series.